All right, welcome to the last section of Chapter 2. Finally, we're getting this out of the way here. We're going to be looking at solving inequalities. So the last section we dealt with solving equations. So there's a lot of rules in solving equations that don't get to be used when we solve inequalities. Now, we're going to start off with just really what does it mean? And then we're going to go into the polynomials, the easy ones that we should be able to look at them graphically more than any other way. And then some other functions that get a little bit more crazy, and you might not know the graphs of them right off the top of your head, so we have a different method or a different strategy in order to solve them. All right, so first, what does this statement mean, or what do these four statements mean? That's kind of our big first question. It seems to me that this is the question that actually gets most people struggling when we begin looking at solving inequalities. Now, we understand what it means for x is greater than 3. This tells me that we're looking at all numbers on a number line. So we're looking at this number line, we're starting at 3, and we're not using 3 but getting bigger. So we're looking at all these numbers to the right of 3, but this is just an x value. Here what we want to look at is the function. Where is the function bigger than 0? And we like to compare it to 0. That's why I'm specifically using 0 here. We can't usually say where is the function bigger than 4, because what we do is we set it compared to 0 and then we solve from there anyway. So what we need to do is we need to understand graphically what do these four statements mean. And we're going to look at this just as a graph. You have to remember that f of x means the same thing as y, which means we're asking where are the y values bigger than 0? And that's everything up here. This, in quadrants 1 and 2, all of this is where f of x is greater than 0. Right? That should be very straightforward. Then we can ask ourselves, where is the function less than 0? And that would be the y values, and that would be the y values below the x-axis. So down here in quadrants 3 and 4, this is where my function is less than 0. And then the obvious one should be, where is my function equal to 0? That would combine with this greater than or equal to or less than or equal to, and where the function is 0 is on the x-axis. So if I was to look at some sort of graph that looked something like this, and I said that this was A, and this was B, and this was C, and I asked, where was this function greater than 0? I should be able to look at this graph and say, oh, it's everything above the x-axis. So that would be between A and B, and everything bigger than C. And because I don't want to know where it's equal to 0, I would write this in interval notation as going from A to B, not inclusive, union, going from C to infinity. So notice it really has you really need to know where your x-intercepts are. Well, the very first problem I'm going to give you is a polynomial. We're not going to use a sign chart just yet. I'm going to show you how to use that in a little bit. But I want to look at this graphically first, without using a graphing calculator. I want to determine the real numbers of x that cause f of x to be 0, positive, and negative. So first question is, where is the function greater than 0? So I feel that all of us should be able to graph this polynomial without the use of a graphing calculator. we know that x equals -3 is a 0. We know that x equals 4 is also a 0. And x squared plus 1 has no zeros. So we have zeros at -3, and we have 2 of them at +4. Well, this is a degree 5 polynomial. There's 2 of them here, 2 of them here, and 1 of them here. So my degree is 5, which means graphically it has to do this. It's going to look a little bit like a cubic. And because this is a multiplicity of 2, it's going to bounce on 4. We can figure out that our y-intercept is going to be 48 by plugging in 0. So 4 times 4 times 3 is 48. So we have a y-intercept way up here at 48. And graphically, it's going to look like this. It bounces off of that 4, and it goes down forever. So in order to answer this question, I want to know, where is the function bigger than 0? So I'm looking at above the x-axis, and I know it's above the x-axis. Notice I don't care about when it equals the x-axis. It's above the x-axis from -3 until 4. It's 0 at 4, so I don't get to use that as an answer, but then it is continually positive after 4 all the way to infinity. But then I can go ahead and answer all 4 questions here. The second one being, when is it greater than or equal to 0? Well, now that I want it to be equal to 0, now I can use -3. And I can use 4, which means it's going to be from -3 all the way until infinity. And our third question here is, where is it less than 0? Well, it's less than 0 below the x-axis, so therefore it's from -infinity up until -3, not using it because that's where it equals 0. And lastly, our last question would be, where is it less than or equal to 0? And that's when we got to use the bracket on -3. So notice the 4 different answers here for the 4 different questions that you're going to be asked. Now, note I did give this one in factored form. And let's go ahead and look at what this would look like on what we call a sign chart. So a sign chart is a simple number line where we put the zeros of the polynomial. So in this case, -3 and 4. This is what we do. We say, okay, from -3 and +4 are the only zeros of my function. So I go at -3, I get 0, and at 4, I get 0. So what I want to do is I want to test some points between, or in these intervals that I've broken the line into. So to the left of -3, let's say -4. That's just a number that's in this interval. And then I can say, okay, what's another thing inside this interval? Well, 0's between here, so I like to plug in 0 whenever I can. And a number bigger than 4, let's say it's 5. Now, the reason we can do a sign chart is this way we didn't have to look at the graph. But I think with polynomials, I want us looking at graphs more than I like the sign chart, because this, you get to understand what the shape of the function looks like. So if I was to plug in -4, I would get -4 plus 3, which is negative, times -4 squared. Well, that's positive. That means everything in this side, in this middle thing, is going to be positive. And -4 minus 4, well, that's going to be -8, but squared is going to be positive. So negative times positive is going to be negative. So everything in this interval is going to be negative. And look, that's actually what happens in the graph. Everything on that interval is negative. It's below the x-axis. If we were to plug in 0, we already know because that's going to be positive 48. But if I plugged in 0, I'd get positive times positive times positive, and that's positive. And if I plugged in 5, I get positive, positive, positive again, and therefore the whole thing is positive. And look, that's actually what our graph tells us. Here it's negative, between -3 and 4 it's positive, and bigger than 4 it's also positive. All right, we're going to use sign chart exclusively for the last set of problems that we come up to. But for polynomials, I think we're going to look at the graphs more than anything. So let's say I was to give you a problem like this. 2x cubed minus 7x squared minus 10x plus 24 is greater than 0. Now, in order to solve this problem, you're actually going to need to factor. Well, we've dealt with this all chapter long on how to factor polynomials of larger degree like this. And we have to use our possible rational roots. So we have to look at all of our possible zeros. We have to think about it in synthetic division, and you'd get these three numbers as your zeros. Now that's through doing some work, but just to save us time, let's say you've done all that work. You've gotten these three zeros, and now I want to look at this graphically and look at -2, 1.5, and 4. Knowing those are my zeros, I can now graph this function. We also know that the y-intercept is 24, so that helps us solve that a cubic function is going to look like that S-turn, and it's a positive cubic, so it's going to be down here, it's going to go down, and it's going to come back up. And this is just a rough sketch, but the rough sketch is all we need in order to answer this question. So in this, we want to know, where is it bigger than 0? And we know it's bigger than 0 between -2 and 1.5, or 3/2. And it's bigger than 0 from 4 to infinity, because that's where it's above the x-axis. We want above the x-axis here. And if it was greater than or equal to 0, we would just add the square brackets to all three of these numbers. So that gets the little infinity sign there. All right, x cubed minus 6x squared is less than or equal to 2 minus 8x. We could solve this one graphically just exactly as it looks, but I like to get everything to one side and set it less than or equal to 0. If you were to graph this function, now let's say you couldn't factor it, and if you were to graph this function and find the zeros and observe the graph as we've been mentioning, obviously you're going to write your answer. You would notice that the zeros of the polynomial, now this is a cubic polynomial, and it looks like none of my zeros were negative, so they were all positive. It was a cubic polynomial, so it looked something like this. And here was 0.32 using my graphing calculator, 1.46, and 4.21. And I asked, when is it less than or equal to 0? Well, it's less than or equal to 0 from negative infinity up until 3.2, and it's equal to, so we get to use square brackets, and square brackets 1.46 to 4.21. Now, sometimes you're just going to have to use graphing calculator. I can't remember if the book says to use it specifically, but we need to remember how to do things by hand, and we need to remember how to find the zeros on our graphing calculator. So now we get to the ones where we are going to have to use a sign chart because we can't graph these things off the top of our head. So what we want to do is we want to figure out any x values, the numbers that go on our number line here, are the x values that make the numerator 0 or the denominator 0. So we have this function that is 2x plus 1 over, please note that division bar right there. This is 2x plus 1 over x plus 1 times x minus 1. So I'm asking, when is it 0? Well, it's 0 at -1/2. That makes the numerator 0. And then it's undefined at x equals 1 and -3. So those are the numbers I need to use on my sign chart. And I need to make a note of these as I go. So at -3 it's undefined because it makes the denominator 0. At negative 1/2, it's 0 because it makes the numerator 0. And at x equals 1, it's undefined because it makes the denominator 0. And the same as before, the same as that first problem we did, I need to find some values that are in each of these intervals. So here I'm going to choose negative 4. Here I'm going to choose negative 1. Here I'm going to choose 0. And here I'm going to choose 2. So if I plugged in a negative 4, this would be negative 8 plus 1. So that's a negative in the numerator over negative 4 plus 3 is still negative. And if I subtract, that's negative. And if I do negative divided by negative times negative, it's going to be negative. If I plug in a negative 1, negative 1 makes negative 2 plus 1, that's negative, over positive times negative. So positive times negative. So this is negative over negative, which is positive. If I plug in at 0, I get positive over positive negative. Well, that's negative. And if I plug in a 2, I get positive over positive positive, which is positive. Now, one thing I want to mention before we continue moving forward here is do not assume that it's going to go plus minus plus minus, plus minus plus minus plus minus all the time. You notice that very first problem we did was actually minus plus plus. So it is possible to repeat positives or negatives along the way. So if we were to look at f of x is greater than 0, I would look at all of the things that give me positive values. So it's positive from negative 3 to negative half, and then it's positive again from 1 to infinity. But I want to change the statement just a little bit here. Oops. If I was to say less than, then it would be negative infinity. But what if I was to say it's from f of x is greater than or equal to 0? Well, f of x is greater than or equal to 0 says I can now use 0. Well, it's only 0 at 1/2, so this statement is going to change ever so slightly as to say, well, negative 3 is undefined, so I can't use it still. Then I can go to negative 1/2, but I can use negative half because it makes the function 0. And then it's going to go from 1 to infinity, not inclusive. And that's how it's going to change for this particular problem. Okay, so this continues to work for all types of problems. The sign chart is very, very handy, especially for problems like this. Well, this is still irrational. There's a couple other ones that are a little bit more difficult here. If I have 5 over x plus 3 over x minus 1, I must combine these fractions. So I must create common denominators. So this one I need to multiply by x minus 1 over x minus 1. And this I need to multiply by x plus 3 over x plus 3. So here I get 5 times x minus 1 over x minus 1, x plus 3, plus 3 times x plus 3 over x minus 1 times x plus 3. And, we're looking at less than 0. Combine like terms as I add because now I have common denominators. This is 5x plus 3x becomes 8x. Negative 5 plus 9 becomes 4. And now we have a single fraction that we can do our sign chart for. We have negative 3, negative 1/2, negative 1/2, and positive 1. And we would do the same thing as before. Find some values, plug them in, and answer our question. But really the whole point for this problem was to show that you must combine these fractions, you are not allowed to multiply and cancel the fractions like we did with equalities. That was for equations, not for inequalities. All right, so there's your little statements. Combine your fractions with a common denominator and solve as before using our sign chart and answering the question. There are problems like this that look like kind of nothing. They're not really polynomials. They're not rational functions, but they're just other types of functions. And we're going to do the same thing. We're not going to graph the function because we don't need to because we can't do it in our head. But we still look at what are the zeros. The zeros are -1 and 3. All right, so it makes the square root 0, it makes the factor 0. And we're going to say, okay, at -1, let's say if I use -2, 0 in here, and 4 in here. If I plugged in -2, notice that this doesn't exist. So that means this whole statement here, this whole interval, is undefined. It doesn't even get to be used. And then at -1, it's 0. If I plug in a 0, I get -3 times +1, which is negative. And if I plug in 3, I get 0, which is 0 here. If I plug in a 4, I get 4 minus 3 is positive. 4 plus 1, square root is positive, so it's positive here. And now look at this answer here. This is looking for greater than or equal to 0, which means I want this. And I want this, and I want this. I want the -1 because it equals to 0. So we're used to writing the 3 to infinity. That's okay, but what are we going to connect it to? There's no interval. Well, if there's not an interval and it's only a single value, we're going to use the squiggle brackets and say -1 squiggle bracket. That's just a set with a single piece in it. All right, so there's the answer for greater than or equal to 0 on this particular function. So there you have it for something a little bit nicer than my writing. And what I think is the last problem here as we continue forward is the x minus 2 divided by the absolute value of x plus 3. Well, same thing. Number line, sign chart, I get to use -3 and +2. So I choose some values, choose some values, choose some values. And we look at -3 is undefined because it makes the denominator 0. 2 makes it 0. So I guess start plugging things in. Plugging in -4, I get negative over positive. And guess what? Everything is going to be positive in the denominator because it's the absolute value. So I'm going to get negative. If I plug in 0, I get negative over positive. So this is negative. And if I plug in 3, I get positive over positive. So it's positive. I want to know where is it less than or equal to 0. All right, so less than or equal to 0 is going to say from -infinity up until -3 parentheses because it's not used. You can't use it on an undefined term. Union -3 to 2 with a bracket because that's where it equals to 0. All right, that is going to finish us off for 2.9. Also, it's going to finish us off for Chapter 2, so we can get out of the Algebra 2, Algebra 3 kind of things, and right into the trigonometry by the end of the week. All right, I hope you guys learned some stuff. I hope you guys use it. I will see you guys tomorrow.